Hi everyone, my name is Heng and I'll be presenting on my final year project on computational models for metaphor understanding. A metaphor is a figure of speech used to make the language more vivid and expressive. Metaphor understanding is a complex task for natural language processing (NLP), as it involves recognizing analogies and making inferences between non-literal concepts. For example, the world as a stage is a metaphor because the world is not literally a stage, but the comparison is used to convey the idea that life is a performance or a series of roles that we play. Metaphor understanding consists of two sequential subtasks: metaphor identification, followed by metaphor interpretation. Using this example sentence, metaphor identification involves determining if this particular word in the sequence is literal or metaphorical. Metaphors are then classified as 1 and non-metaphors as 0. Then, metaphor interpretation can be conducted to paraphrase the identified metaphors to their literal meaning. In this example, the literal meaning for handle is manage. So currently, there's not much research done on metaphor interpretation due to its complexity. This project aims to focus on the metaphor interpretation subtask and proposes two models based on different training paradigms, namely classification and mass language modeling. Thereafter, a detailed evaluation is conducted to compare the strengths and weaknesses of both models in terms of general performance and generalizability on unseen words and multi-word expressions. For the first paradigm, we formulate the metaphor interpretation as a classification task and treat each paraphrase label as one class label, no matter if the label is a single word or multi-word expression. With our dataset, there are around 7,000 class labels. For each given metaphor, we aim to classify it among the 7,000 paraphrases. The models are then evaluated using a candidate label set, where each metaphor has a positive label and three hard negative labels that have similar meanings but are not correct in the particular context. On first glance, it seems like a sequence classification task. However, we tweaked it slightly for this use case. Instead, the last hidden state of the Roberta transformer is extracted. Then, using a metaphor mask, we extract the embeddings at the metaphor positions in the sequence. Finally, we average the embeddings and feed them into the classification layer for prediction. Moving on to the second training paradigm, this time we formulate the problem as a masked language modeling problem. During training, we replace the metaphors with a masked token and then concatenate the original metaphor at the end of the sentence. The correct label for the masked token will then be the paraphrase label instead. This time, we use the original language model vocabulary size of 50,000 to train. During evaluation, the output logits at the mask positions are extracted, and then we compute the probability for each label in the candidate label set using the extracted logits. The main difference from the classification paradigm is that this masked language modeling approach enables the model to take in unseen labels. So here are the evaluation results for both models with the various transformer models. Accuracy is used as the evaluation metric. We focus on the best performing transformer model, Roberta, and we can see that the classification approach gave the best overall accuracy, while the mask model performed better for unseen labels, therefore is more generalizable. So before ending, I've prepared a simple web user interface and deployed both models to give a better visualization. So here is the simple web UI that I've made to deploy and to visualize the models. So over here you can see that both paradigm 1 and 2 models are being selected. You can choose either one of them or both. And then over here you can see that there's a drop down with a few examples for reference purposes and also custom, which means that you can input your own text and labels. So the example sentence over here is I managed to get whole, which is the metaphor denoted by the X and the underscore of this limited addition bag. And then below over here you can see that these are the candidate labels, which are 4 labels, 1 positive and 3 hard negatives. So take note that because task 1, the classification model is being selected, so the class labels have to be part of the predetermined 7,000 labels, therefore it's in a drop-down format. So one of these must be selected. So let's click submit and see what are the results. So over here you can see that these are the probability scores for each of the labels, and then the highest probability is being highlighted in yellow. So in this case we can see that both models managed to correctly predict the positive label. And then moving on to this task 2 processing below, notice that get whole is a multi-word expression with 2 words. So in task 2, these two-word metaphor is being split into first sentence being the get is replaced by a mask, and second sentence the whole is being replaced with a mask. So this to visualize how the processing works, and then after that the results are aggregated as shown over here. So we may want to look at a custom example now. So maybe we can do example sentence such as the comedian convulsed the children with his jokes. So over here you can see that the comedian make the children laugh very loudly as if they are convulsive, but the children are not literally convulsive. So in that case the positive label will be amused. We can put it as amused. Negative label will be something similar to convulsed but not correct in this context. Maybe shuddered, shaked, or rocked. So with this we can submit, and then we can over there see that the task 2 model managed to predict the positive label correctly with the highest probability, and then here are the probability score for all the other negatives. So yeah, that's come to conclusion of the presentation. Thank you so much.